All right, gang, Math 5500. Going to dive back into model assumptions and dig deeper into regression diagnostics. Remember, classic test question. What are the four model assumptions for regression? I mean, that's something that you just almost got to predict that's going to happen one day. So again, linearity, homoscedasticity, independence, and normality. The examples that I've run through previously have been small data sets. So sometimes we get wacky plots, with small data sets. And again, the small data sets were created by design just so I could make some points. But let's let's get out of this and let's dive into a data set that I have already loaded. Now, what we have here is called assessment, state assessment, and what they've done, they have some sort of end assessment that I have no idea how that's measured. It's kind of like my daughters took an AP, a couple of AP tests last year. They did really well. They scored fives, and I was telling my mom, well, the girls scored five on their AP, and she's like, well, that's not very good, because she was thinking, 5 out of 100, which wouldn't be very good. But as we know, AP five is really good. So again, I don't know what this is measured on. I don't even know what the range of scores are. And I can tell you right now, that's going to get on my nerves typing that out. I can't do that. Okay, sorry. Let me GLP YR. No, that's not right. DPLYR. Yeah. Let me load that, and I want to rename that. That's going to get on my nerves. It's easy to do. If I can find the commands. So rename, and I want to just call it end instead of end assessment. All right. So now if we do head data, all right, much better. So what you can see is we have this end assessment that ranges from about zero point 0.5 to about 15 or so. So I guess the scores run from 0 to 15 or whatever. This has the age of the students, so you can see that we're probably dealing with school-age kids, 3 to 19. So yeah, all the way down to preschool. Okay. We also have a state score. I don't know what the state score is all about. It has a range from 45 to 81. So maybe from I don't know. So high socioeconomic status, dichotomized, either yes or no. Gender, male, female, and private school. I assume that's they attended a private school, or they did not attend a private school. So kind of a I don't know, semi-interesting data set here. If you're interested in predicting state assessment scores, end assessment scores from age, state, economic, socioeconomic status, and so on and so forth. Now, I don't even know the. I probably have to attach data. All right. All right. So we have 725 students. So we have a large data set. So again, let's just say that I would like to focus in on using the state score to predict the end score. So I'd probably want to first of all just look at the correlation between state and end, and it's an extremely high correlation, 0.91. Next thing I'd probably want to look at is a scatter plot. And a scatter plot shows, without question, a linear tendency. So I have no problem moving forward, at least from the eyeball test, moving forward with using the state score to predict the end score using a linear model. That's just that's just from I hate to sound like a nerd, but from a regression statistician perspective, that is just beautiful. All right, enough of that. All right, so let's get into the model, and we will. So end predicted by state, and then summary. And we all know that we're going to have statistical significance of our predictor at the 0.001 level. The reason I know is we have so much power to be learned in 6610 and 6620. Power is just the probability of rejecting a false null. And as your sample size goes up, you get increased power. So I had no doubt that my cat is losing its ever-loving mind. We have a lot of cat drama in these videos, don't we? But anyway, we have a lot of power, so no doubt that we would achieve statistical significance for that predictor. I would like to now dive in. Look at the model ANOVA. Again, it's not going to vary from the one predictor because the model is the one predictor, and we only have one predictor. There's no difference. Model really, the ANOVA table really starts to play a role when we get into multiple predictors because it's a model diagnostic. Okay, next thing I want to do is look at my plot, so I know I can just do plot of my model, and we get all this cool stuff here. At least I think it's kind of cool. So let me scrunch this over where you can see it. So now this is the kind of stuff we want to see. We have a shotgun blast of our residuals mapped over our fitted values. Notice that the red line is relatively straight, relatively flat. So that says that we have equal variances of our residuals. Next thing we see is, again, this is just beautiful to the eye if you're a statistician. Theoretical quantiles match almost perfectly with the student standardized residuals. I was actually taught that well, we'll get into that later, maybe, I don't know. But anyway, you can see that the points, there's a little deviation up in the upper theoretical quantiles, but yeah, I see no concern there. So again, another examination of fit of linearity. We've got a red line that is relatively straight. We have a little bit increasing variance in the end, but certainly nothing to raise a red flag. And then we get into our residuals versus leverage. We get into our Cook's distance, which is to be learned later. And I will tell you that this is just this is solid stuff. So in terms of moving forward, with the diagnostics that we currently have, I would feel very, very, very comfortable in doing so. All right, now it's time to add to our bag of tricks, our toolbox, if you will. So we're going to dive deeper, and I want to focus on three things. I want to focus on outliers, which are large residuals. I want to focus on leverage points, which examines the difference between an X and the mean of X's, and then I will get into an influential point. Now, we're going to get into something called Cook's distance, and there's so many other things. There are different types. There are DF betas and DF fits, and so many different things that we'll study in 6500. But I want this last lesson to be relatively brief because I know that you have a lot on your plate. You have an assignment 3 coming up. You have a final exam that you need to study for. So I don't want to bombard you with a lot of additional information in lesson 7. So I'm going to focus on the 3 biggies. Again, outliers, leverage points, and influential points. And we'll dive into Cook's distances probably in the next video on that. Now, let's go down here. I want you to focus on the points that I have and then let's talk about A, B, C, D, well, A, B, C, 1, C2, D, E, whatever it is. Let's talk about these points. Now, first of all, how would we define A? well, and I'll tell you what, let's just focus on leverage points and influential points. Would point A be a leverage point? Well, again, leverage examines the difference between the x and x bar. So if we have a symmetric distribution on x, we are assuming that probably about in the middle is going to be our the mean of our x's. So any value, yeah, sort of, I don't know. Any value that falls close to the sample mean does not have a large leverage. Okay, so I'm going to say that A and D for sure, and marginally speaking, I would say B is relatively close as well. So E, C1, and C2 would have high leverage because they're further from the mean, for a mean of x's. Now, the influential points, what we do is we try to imagine a line and pretend that's straight, all right? We try to imagine our regression model, and then we try to imagine would these points, would this additional point to that cause the slope to change significantly? Well, clearly E wouldn't. E is just a point that almost falls on the line, so E wouldn't change it at all. So even though E would be a leverage point, it would not be an influential point. Clearly C2 would want to drag that line down, wouldn't it? So C2 would be a leverage point and an influential point. C1, I would say that that's a leverage point, but I don't think it would change the slope significantly. And B1 as well. Now this D down here, it's clearly not a leverage point, but because of its location, it could shift this line down, but I don't think it would change the slope. It would change the intercept. So this D, I would say, would not be an influential point or a leverage point. So just give you an indication just examples of different things that, in different classifications. All right, all right. We're going to dig pretty deep into the weeds now and get into some theory, and so we need to set up a few things and recall a few things. Remember that the variance of our residuals is just estimated by the mean square error, and the mean square error is an unbiased estimator. Which means that our sample variance of the variance of our residuals, the sample variance of our residuals is an unbiased estimator of the population variance of our residuals. We get into something called a studentized residual. Now, I'm going to mess with this big time later on. And a lot of people refer to it at this stage as a standardized residual, and yeah, I'm okay with that. But anyway, there is a way to standardize our residual, and all you do here is you just think of z-scores. Z-scores have a mean 0, standard deviation 1. They're on a standardized scale. That's kind of what we're attempting to do here. Now, I want to completely shift gears, and I want to dive into this hat matrix because, as I told you before, the hat matrix has two properties. First of all, the hat matrix is called a projection matrix because it projects our y's onto our predicted y's, and it also has these other important properties and characteristics that are useful in model diagnostics. So, that's where we're headed with this, is the latter. Now, okay, I always learned, I've been teaching now, 32 years. Wow, it's crazy. They always tell me never take anything for granted. So let's just start at the bare bones with the hat matrix. We know that we can predict y by taking our design matrix times our beta matrix, right? And we know that the beta matrix is x transpose x inverse, x transpose y. So by substitution, we can and shifting a little bit, we can see that the hat matrix is this matrix right here, again, because it projects y onto the predicted y's. Now, we can examine a little bit further. I don't really know where I want to head with this. We can dive into this a little bit further. Yeah, I do. Let's go this route. We know that our errors are equal to the observed minus the predicted. But now we know that the predicted can be rewritten using the hat matrix, and we know using just a little bit of what we know about multiplying matrices that this can be rewritten as the identity matrix minus the hat matrix times the column vector y. Couple things about I minus h. First of all, it's symmetric. It's an n by n, so it's a rather large matrix. It's idempotent. Let me get over here where I can see. Then we'll spell something wrong. And that the variance of E is equal to this. All right. Now, I want you to recall that, and this is something that I showed in an earlier video, that if we have the variance of x times some column vector v, that we can rewrite this using a property as x times the variance of the column vector v times x transpose. So we can rewrite, therefore, the variance of E as I minus h times, let me make sure I'm on track here, I minus y. Okay, so y is a column vector, so I can do the variance of y times I minus h transpose. Now, we also know, trying to formulate this in my mind where I want to go and what I need to show you. We also know that the variance of E is the same thing as the variance for our y's. And both of these are usually very large n by n matrices. Now, the previous example, data set I used, state assessment, what was it, 740 or 7, whatever. It was in the 700s. 700 by 700 matrix would be extremely large. But anyway, what this would look like, the variance of y would, as we know, on the first term, we would have the variance for y1, variance for y2, and the variance for yn. On the off diagonals, we would have the covariance. For example, in this second spot right here, we would have the variance for y1 and y2. Now, we know that we can predict any y, so y sub I. We can, well, not predict. We can state that the value of the y sub I can be, well, we could predict it by this, but we can make it equal to the x sub I by adding an error term. So we therefore know that the variance of our y sub i's would be equal to the variance of our x sub i's beta plus our e sub i's. And then we can separate this, so the variance of our x sub i's beta plus our variance of our e sub i's is equal to, well, that's not right. No, we've got to have 2 times the covariance of xi betas ei's. I almost forgot that term. Um, now, uh, okay, let me pump the brakes. You guys are probably sitting there thinking, what the hell is he doing? Uh, recall, all right, let's put this in this box. Yeah, that just came out of nowhere. That's not going to make any sense if I don't. There's a property that says if we have the variance of like ax plus by, that this will be equal to a squared variance of x plus b squared variance of y plus 2ab covariance of xy. Okay, so I think it's pretty clear why we need to implement this in this case, because we're taking the variance of a sum. And then I think it's pretty clear where the covariance term actually comes. Well, this works out really nicely because, first of all, we know that the variance of b is just 0. I mean, b is what? It's a true value. It doesn't vary. It's 2 or 12. No variation. So we know that the variance of b is equal to 0. And we know that up here, we know that these x's are not correlated with the betas. So we know that this relationship has to be 0. This variance has to be 0. So we end up with 0 plus the variance of e sub I plus 0. We end up that the variance of our y sub i's is equal to the variance of our e sub i's. So important to keep that in mind. So that brings us to that the variance of E is equal to I minus H, the variance of Y, I minus H transpose. It'd be really helpful if you guys could see this, wouldn't it? And this is equal to sigma squared times I minus H times I minus H transpose. And since I minus H is idempotent symmetric, we know that this gives us just I minus H. Now, we never know the true variance of any particular error, because again we're estimating sigma squared with the mean square error. So we estimate the variance of some e sub I by the mean square error times I minus H. Now, drum roll please, all right? Okay. Why are we going through all this? Well, we know that the hat matrix is an extremely large matrix, and we can focus in on these diagonal elements. These diagonal elements turn out to be extremely important to us in model diagnostics. So we can say that HII is the ith diagonal value. So what this would allow us to do, it would allow us to focus in, for example, on the 5th case, or the 7th case, or whatever number. I just chose 5 because my birthday is in May, and I chose 5. That's scientific. So I could come in and look at, for example, the variance of our 5th residual by taking the mean square error times 1 minus the diagonal element in the 5th place. From this, we can create something called the studentized Did I spell that right? Yes. Residual. It's the reason I didn't talk much about that before, because I knew this was coming. Uh, and we calculate this by, well, how do we calculate it? We take the error over the square root of the variance. All right. Whatever that means. I'm done. Take care. We'll put all this we'll put all this to work in the next video.